Hey guys, today we're going to talk about finding the equation of a tangent line. We've been talking about derivatives, and yesterday we looked at the power rule and some of our basic derivative rules. So now we're going to apply that to how we find a tangent line. Remember, we talked about how the derivative is actually the slope of the tangent line. Well, that's true if it's talking about a point. So we actually take a point and we plug it into the derivative, and that will find us the slope of the tangent line. And so we're going to find the equation of the tangent line, and just like any type of line that we find the equation of, all we need is a point and a slope. And if we take a point and a slope, we can use point slope and then find the equation of that line. Okay, so we're going to take a look at a couple different examples. First one we're going to look at is find the equation of the tangent line to the graph of f of x equals x squared when x equals -2. All right, this is a very typical type of question that you're going to see that we're going to deal with trying to find this equation of the tangent line. Well, like I said, whenever we're trying to find an equation of a tangent line, you need two things. We need a point and a slope. Okay, so when finding the equation of a tangent line, you need a point and a slope. All right, so let's start off with finding the point. The point's the easiest thing. All right, when we need to find the point, all we gotta do is take that x value and plug it in to f of x. So we know x equals -2, so f of x, f of -2, would give us -2 squared, which gives us 4. So our point is -2, 4. Now sometimes they actually give you the full point, and so it's even easier. In a lot of cases though, you need to find the point by plugging in that x value into the original function. So we now have the point. Now all we need is the slope. Okay, well, we talked about again that the derivative gives us the slope of the tangent line. So the first thing I need to do is figure out what is that derivative. And so here we have f of x equals x squared, and using that power rule, f prime of x is equal to 2x. We bring that 2 down, we take away 1 from the exponent. So now I have the derivative. Now I'm not done yet. I need to now take that point that I have and plug it in. And notice all I have is an x inside this derivative. So I'm going to take that and do f prime of -2, which gives me 2 times -2, and my derivative is -4. That gives me the slope of the tangent line. So our slope now is -4. So I have a point and a slope. Again, the easiest way to make an equation of a line is use point slope. So remember, point slope is y minus y1 equals m times x minus x1. This is why we practice this all in chapter P, because all we have to do is plug in our point and our slope, and our equation of the tangent line is just going to be y minus 4 equals -4 times x minus -2, which is plus 2. And there we have it. There's our equation of a tangent line. Okay, so not too difficult. All right, we're going to do this a lot this year. All right, equation of those tangent lines are one of those big questions that we see over and over again on the AP exam. So we'll keep looking at these. All right, let's take a look at another example. All right, switch it up a little bit here. All right, this time we're going to do tangent line to the graph of, let's just switch our function, and let's make it a little bit more exciting. Let's use little trig, because everyone loves trig. 2 sine of x when x equals pi over 3. So got that unit circle going on here. We got to do all the same stuff that we did in the last problem. We need two things. We need a point and we need a slope. All right, so the point, we're going to take that x value, we're going to plug it into our y equation here, so we know x equals pi over 3. Y is going to equal 2 sine of pi over 3. And so we got to think back to that unit circle. What is sine of pi over 3? Well, that's going to be square root of 3 over 2. 2's cancel out, so now y equals just square root of 3, and our point is now going to become pi over 3 square root of 3. So there's our point that we needed. All right, now we're going to go to the slope. And again, remember the slope comes from the derivative. So let's take the derivative of this. Now, we learned the derivative of sine and cosine yesterday. 2 here is in front of sine. This is a constant multiple. And remember, with constant multiples, they don't affect the derivative. They just get multiplied by it. So here, y prime is going to be 2 times, what is that derivative of sine? Derivative of sine is cosine, so we're going to go ahead and put cosine right next to it. And there's our derivative. So now we got to go ahead and take that point, because we're not done yet. We can't just say this is our slope. We need an actual value, a number. So we're going to take that x and plug it in for our x here. So y prime, and there's a lot of ways to write this. You'll see this written actually as just pi over 3, almost like a function. All right, some people will write at that value, but I'm going to write it like that for now. 2 cosine pi over 3. So we need to know what cosine of pi over 3 is. We can't leave it like that. Cosine of pi over 3 is 1/2. So 2 times 1/2 is going to give us 1. And now we have a point and a slope. Let's use point slope. We're going to plug it right in there. Y minus our y value is square root of 3 equals 1 times x minus pi over 3. Okay, so there's our equation of the tangent line. Now, one thing I want to go ahead and go over. That's a perfectly acceptable answer when we get to free response questions. Okay, I leave it like that every single time, but you know, a lot of these questions are going to show up on multiple choice tests. All right, on the AP exam, this is probably going to be a multiple choice question. And you're probably not going to see it like this. They're going to go ahead and start doing some different simplifying to it. So let's see what kind of simplifying we can do with this. All right, for starters, we really don't need the 1 or the parentheses, because even if we distribute it, it's going to be the same thing. So y minus square root of 3 equals x minus pi over 3. One of the main things they're going to do, you know, they don't like fractions as much as you guys don't like fractions. All right? It's really a pain to type fractions in on a test. So they're going to get rid of the fraction. And the way that we get rid of the fraction is multiply this entire equation by 3. And so if I multiply that entire equation by 3, I get 3y minus 3 square root of 3 equals 3x. Now the 3 cancels here to give me pi. So you may see that as an answer choice. But a lot of times, even that, they'll keep going. A lot of times they like to put the x and the y on the same side and all the constants on the other side. So what I'm going to do here is actually add the pi over to the other side. And I'm going to subtract the 3y to the other side. So that's going to give me pi minus 3 square root of 3 equals 3x minus 3y. And that's most likely what you're going to see on an AP exam multiple choice question. You're not going to see the fraction. You're going to see them work through it like this. Get rid of the fractions and then group all your variables to one side. Why they do it, who knows, but that's how you typically will see it. So you want to make sure you're practicing being able to get rid of those fractions. All right, let's take a look at another example. And this one's going to be a little bit different, but it kind of talks about the idea of tangent line and slopes. We're going to see if we can find a specific place where a tangent line has a specific slope. All right, so let's see what we can find here. Find all values of x for all points on the graph of f of x equals x cubed minus 2x squared plus 5x minus 16, at which the slope of the tangent line is 4. All right, so now what we're actually looking for is where does this function have a tangent line where the slope is 4? So, well, what do we talk about with the slope of the tangent line? The slope of the tangent line is just the derivative. Well, now we're trying to kind of simplify this out a little bit more. We're trying to find where is the derivative equal to 4. So why don't we take the derivative and set it equal to 4? That's going to be what we do. So let's take the derivative using that power rule here. F prime of x, x cubed becomes 3x squared minus 4x plus 5. And again, the derivative of negative 16, because it's a constant, is 0. All right, so here's our derivative. Now we're just going to have to set this equal to 4. So let's go ahead and take 4 equals 3x squared minus 4x plus 5. And now we solve. Now we got a quadratic. So whenever we have a quadratic, the way that we solve it is we get it equal to 0 first. So I'm going to subtract 4. Subtract 4. So I got 0 equals 3x squared minus 4x plus 1. And now we got to factor this. Okay, and again, I like to factor by grouping. So I'm going to take 3 times 1, which gives me 3 factors of 3 that give me negative 4. This is going to break to negative 3 x and minus 1x. And then I can factor this by grouping. So I can take out 3x here, x minus 1. I can take out a negative 1, x minus 1. And this factors to 3x minus 1, x minus 1. All right, I know it takes a few more extra steps, but I like it doing it because I make sure I'm always right this way. And so I take these two factors, I set them equal to 0, and I get two values, x equals 1/3, all right, and x equals positive 1. These are the x values where the slope is going to equal 4. Now, this particular question, it only asks for the x value, so I'd be done with that, that's all. All right, but what if they asked for the actual points where the tangent line has a slope of 4? Well, if they needed the points, I would have to take those x values and plug them back into my original, but this is a bit excessive. We're not going to do that for this problem. We only have to do the x values. So this right here is my final answer. That's where the tangent line is going to have a slope of 4. Okay, so that's really all there is to equations of tangent lines. But we need to talk about one other topic today, and that's about differentiability and when are things, when are derivatives going to exist and when do they fail to exist? All right, there's 3 big times where a derivative fails to exist. And these are super important. Okay. Let's get rid of this. We're not talking about tangent lines anymore. So when a derivative fails to exist. Okay. When does a derivative not exist? And this would be the same type of case as when we talked about limits that did not exist. But remember, a derivative is a limit. So some of the things that worked with limits also work with derivatives. Like our first one here. Okay? Our first reason when a derivative would fail to exist is when a function is discontinuous. All right, when a function is discontinuous. Now, a limit was able to be discontinuous and still have a limit. That was okay. But with a derivative, if it's discontinuous, the derivative does not exist at that point. So for example, f of x equals 1 over x. Okay, we've looked at this graph a lot. Just a reciprocal graph. And here it's discontinuous at x equals 0. So f of x is discontinuous at x equals 0, so the derivative would not exist at x equals 0. Does not exist at x equals 0. Now everywhere else on the graph is continuous. Here on the right side, anywhere over there, we can find the derivative at. Over here on the left, we can find the derivative at, no big deal. But at x equals 0, since there's no point there, we can't find a derivative at that value. So the derivative does not exist at the spot where a function is discontinuous. All right, let's take a look at another one. All right, our second reason why a derivative would not exist is probably the most important. We see this all the time, is when a function has a sharp turn, or you could also say a sharp point. Whenever a function has a sharp turn or a sharp point, that derivative would not exist there. The reason because, all right, let's look at a function real quick. Most common would be absolute value of x. All right, that makes our v shape here at 0. Well, that point of the v would be considered a sharp point or a sharp turn. And the reason why the derivative doesn't exist is because the derivative from the left doesn't equal the derivative from the right. All right, and this really ties back to limits. Remember we talked about if the limit from the left doesn't match the limit from the right, the limit doesn't exist. Well, derivatives being limits, if you found the derivative from this line, remember it's just the slope of a line, well that slope would be -1. But over here, the slope is +1. And those slopes don't match when you get to x equals 0. So here, at x equals 0, the derivative doesn't exist. Again, anywhere else on this graph, totally fine. All right, there's no other sharp points. There's no points of discontinuity. Everything else is fine, but x equals 0, there is no derivative. All right, and our last reason, number 3, and number 3 is a little bit harder to spot unless you have a graph or know the function. But it's when a function has a vertical tangent line. All right, well, think about it. What is the slope of a vertical line? It's undefined. The slope of a tangent line is the derivative, so that means the derivative must be undefined if it has a vertical tangent line. One of the most common ones that we see is f of x equals the cube root of x. And you may not remember what this graph looks like off the top of your head, but it has this kind of S shape and then goes down and up. But right here, for a brief second at x equals 0, there is a vertical tangent line. And really I could even draw that a little bit better. And you see that the graph gets vertical right there at x equals 0. And if you were to draw that tangent line through that, you have a vertical tangent line. All right, so at x equals 0, there is a vertical tangent line. So the derivative does not exist at x equals 0. Remember, anywhere else on the graph, totally okay, but at x equals 0, it does not exist. Okay? Those are the three big reasons why a derivative doesn't exist. All right? And so one of the big things we get out of this, okay, out of all three of these, the most important thing is differentiability implies continuity. I've had this board up here all year long. Okay, and it will continue to be up here all year long, but differentiability implies continuity. All right, if they tell you something is differentiable, that means that function has to be continuous. All right, because we know a derivative only exists when a function is continuous. All right, it can't be discontinuous and have a derivative. So as soon as you see the word differentiable, we know that function is continuous, and that applies to everything we learned back in section 1.4 on continuity. All those rules of continuity go along with that. All right, so that's really all we need to look at today in terms of derivatives, tangent lines, and differentiability. All right, you guys are going to be working on an assignment in your homework, and you'll also be looking at the front page of a packet trying to figure out when something is differentiable and continuous. All right, so good luck with that, and I'll be back in a couple days to go over any questions.